Hello everybody, my name is Ömer Penek and I'm going to talk about the observation of CNO cycle solar neutrinos in Borexino. To start with the introduction and the motivation, we're asking ourselves how is the sun fueled and how are solar neutrinos created, and the answer to this question is nuclear fusion processes. So in the sun we have the so-called proton-proton fusion chain with a branching of 99% and the carbon-nitrogen-oxygen cycle with a branching of less than 1%. The CNO cycle is the main energy production process in heavier stars compared to the sun. And especially in sub-processes, we get the emission of neutrinos. For example, in the case of the CNO cycle, we have nitrogen 13, oxygen 15, and fluorine 17 decays, which lead to the so-called CNO neutrinos. And in Earth, we have a solar neutrino flux of about 65 billion neutrinos per centimeter squared second. The CNO cycle is directly linked also to the so-called metallicity problem. Metallicity is an input to the standard solar model. A metal is an element above helium, and we can quantify this with the metal to hydrogen ratio. And there are two ways to describe them. There is the older high metallicity or HZ description and the newer low metallicity or low Z description. And the solar metallicity problem is actually the so-called helioseismology is consistent with the older high metallicity description, but in tension with the newer low metallicity description. And if you look to the table in the bottom, we see the solar neutrino species, and here on bottom you have the CNO cycle. We have the high metallicity prediction, the low metallicity prediction, and the relative ratio between them. And we can see that for the CNO cycle, the difference is in the order of 30%. So the CNO measurement can unravel the so-called metallicity problem. Coming to the Borexino experiment, Borexino is a liquid scintillator detector located at the Laboratori Nazionali del Gran Sasso in Italy, and it has an onion-like structure. And so inside we have the liquid scintillator. Then we have a nylon inner vessel, a nylon outer vessel. We have the stainless steel sphere, which is actually holding the 2200 PMTs. And outside we have the water tank, which is important for the Cherenkov muon beetle. The main detection principle in Borexino in the liquid scintillator is elastic scattering on electrons. The Borexino detector is located at Hall C of the NNGS lab, where we have a huge muon shielding. The suppression is in the order of 10 to the 6. To give some numbers, the light lead in Borexino is 500 PE per MeV in 2000 PMTs. The energy resolution is 5% at 1 MeV, and the position resolution is 10 centimeter at 1 MeV. The hardware threshold is 50 keV. The analysis threshold is in the order of 200 keV, and our active scintillator mass is 280 tons, while we apply a fiducial volume or software cut in our analysis with a radial cut of 2.8 meters and an asymmetric Z cut of -1.8 to 2.2 meters. So this corresponds to 71.3 tons. Our signal and background distribution in Borexino, so in red here, we have the energy spectra of all the backgrounds and solar neutrino signals. So you can see basically on the y-axis the counts per day per 100 tons. Per energy, and on the x-axis the energy. So you can see that basically this goes until 2.6 MeV. In red, the solar neutrino species. In violet, we have the internal background distribution, so carbon 14, polonium 210, krypton 85, bismuth 210. Then we have in blue the external backgrounds. These are contaminations coming from outside the scintillator. For example, from the contamination of the PMTs, these are potassium 40, bismuth 214, thallium 208, and then we have also cosmogenic backgrounds. These are due to muon spallation on carbon 12, and this actually brings me to the so-called TFC algorithm. The Borexino collaboration has developed the threefold coincidence veto technique in order to tag the carbon-11 events. And basically, if we have muon spallation on carbon-12, we get neutrons and carbon-11, and these neutrons are captured within 455 microseconds. And on the other hand, we have the carbon-11, which is a beta plus emitter. So basically what this TFC algorithm is doing, it's calculating for each event the probability to be carbon-11, and then dividing the total exposure into a carbon-11 subtracted and carbon-11 enriched spectra. And there is also a TFC paper which went out. It can be found in this archive link here, and there will be also a poster by Alessio Porcelli at 1st of September. So the observation of CNO cycle solar neutrinos is covering the so-called Borexino phase 3, which went from July 2016 until February 2020 and has an exposure of 1,072 days times 71.3 tons. And the analysis range is 0.3 to 2.6 MeV. And actually what is so challenging is the spectral correlation between the CNO recoiled electron spectra and the PEP recoiled electron spectra and the decay electrons of bismuth-210. So this can be seen here. It's by eye visible that the shapes look quite equal. And also if you do a toy Monte Carlo study, leaving the 3 parameters of CNO, PEP, and bismuth-210 free, you can see that the correlation coefficient among them is on the order of almost 100%. So basically, however, we can constrain the PEP neutrino rate with 1.4% precision by doing a global analysis of solar neutrino data and applying the luminosity constraint. This is this publication here. And then we end up with 2.74 plus minus 0.04 counts per day per 100 tons in rate. What is more challenging is the so-called bismuth-210 constraint. And actually this brings me to the slide where how we can actually determine the bismuth-210 rate. And bismuth-210 is actually following this decay chain here. So the mother of the decay chain is lead-210, and we know that bismuth-210 decays to polonium-210, and polonium-210 is an alpha emitter. So in the secular equilibrium, we know that bismuth-210 rate and polonium-210 rate must be equal. And on the other side, polonium-210 alphas are monoenergetic, and in Borexino we have an event-by-event pulse shape discrimination technique based on multi-layer perceptron discrimination variable. So however, life is not that much ideal, because in Borexino we had temperature gradients present in the detector that caused convective motions of the polonium-210 present at the nylon vessel to move inside the scintillator. So you can imagine you have the fiducial volume here, and then you have an extra source, and then polonium is basically moving inside the fiducial volume. So you have an extra source, and this is actually quite challenging to identify the bismuth-210 events from the correct polonium events. And actually you can see here the seasonal variation of the polonium, and basically at some point the seasonal variation drops, and this is basically here you can see this is the starting of the phase 3 basically. And the solution of this problem is actually a thermal insulation and an installation of an active temperature control system. So you can see here the Borexino detector with double layer of mineral wool. Then here you have temperature probes which have been installed around the detector with a resolution of 0.07 degrees of Celsius. On the bottom you have a fluid dynamics simulation which is equal to the measurement basically from 2015, and you can see basically you can basically see the stability of the temperature here. And in phase 3 we have identified a clean polonium region to be used to get the bismuth-210 rate, and this is what we call low polonium field. It's a 20-ton area or volume corresponding to 20 almost 20 cubic meters, and can be modeled by an ellipsoid here. The model is given here with some parameters. One is the minimum rate of the polonium, then we have efficiency factors of energy and the MLP variable, which is important for the alpha selection, and then there is also the beta rate after the alpha selection, since we don't have perfect alpha selection. So basically you can, on this slide you can see the data alignment. So by doing a paraboloid fit, so the low polonium field is around 80 centimeters above the equator. This is an aligned data set. What I mean by aligned data set is basically it's important for bias reduction. So you basically fit the data using an ellipsoid or spline model monthly, and then you extract the Z position over time, and then you create an aligned data set. Basically, you shift the data according to the Z0 from the previous month, and then you can determine the polonium rate and thus the upper limit on the bismuth rate. So this is actually the Z distribution over time is shown on this plot here. So you can basically see here the development of the low polonium field. On the other hand, so the low polonium field, as I said, is 20 tons big. However, we want to apply it in the whole fiducial volume, which is 71.3 tons. So we have to ask ourselves, is the bismuth rate homogeneous in the fiducial volume? And for that, we have to compare the angular distribution and radial distribution of events, homogeneously distributed or uniformly distributed in this volume, and compare it to the data, and we found out that the bismuth rate is homogeneous in the fiducial volume, and this is basically valid within an uncertainty of plus minus 0.59 and plus minus 0.52 CPD per 100 tons in angular and radial distribution respectively. So basically, combining all the uncertainties we have, so we have the uncertainty from the fit, we have the uncertainty due to the mass, due to binning, the angular and radial distribution, which I showed on the previous slide, and also the beta leakage, so the beta rate after alpha selection. If you combine all of these uncertainties, we get an bismuth rate of, so this is the mean value of 11.5 plus minus 1.3 CPD per 100 ton. And this we can actually use in order to constrain it in the fit by doing a semi-Gaussian. So we do a symmetric Gaussian constraint on the PEP neutrino rate and a semi-Gaussian constraint and do a multivariate fit. So we fit simultaneously the carbon-11 subtracted spectrum, the carbon-11 enriched spectrum, and also the radial distribution of events in the region where external backgrounds dominate. And you can see that basically the total fit p-value is in the order of 0.3, which guarantees a good consistency of data and the model. So on the other hand, the CNO measurement can be nicely extracted by doing a profiling. So do a delta chi-square profile versus the CNO rate, and you see in the dotted line is basically the statistical only delta chi-square profile, and the solid line is the one when you smear the systematics. On the other hand, we have also we did also a counting analysis where we have plotted here the Poissonian distribution. So this counting analysis has been done in optimized energy window of 0.8 to 0.9 MeV almost, and then we can basically count the events of all the species in the region of interest, and we found out that we have evidence in this narrow energy region of 3.5 sigma from this counting analysis. On the other hand, on this plot, you can also see the low metallicity prediction and the high metallicity prediction, and we disfavor low metallicity at 2.1 sigma, combining beryllium 7, boron 8, and CNO measurement only. So basically, our best fit values are shown here. So we have a discovery potential from the profiling of 5.1 sigma, and this is clearly a CNO discovery. On the other hand, we did also a toy Monte Carlo study. So we have created pseudo dataset and injected the CNO neutrino rate or with and without injected CNO rate. And we fit these data sets, leaving the CNO rate free or fix it to 0. Then we can define a test statistics distribution, which is basically 2 times the log likelihood ratio. And then we can evaluate the p-value. And basically, you can see here on the bottom plot, the statistical only distribution, which is shown in blue here. Then we have also the distribution of the delta chi-square of the test statistics with injected systematics. And here in pink, you have the distribution of the test statistics with a signal injected at the expected rate we have obtained. So the injected systematics are basically only due to the, mostly due to the response, which is nonlinearity of the energy scale, for example, spatial non-uniformity of the z-axis, light yield, carbon-11 peak position, and bismuth, different bismuth spectral shapes have been also considered. And we come at the end to the result of 5 sigma at 99% confidence level. So this brings me to the conclusion. So ongoing currently is that we want to update the bismuth constraints by taking the data until September 2021. We want to combine Borexino phases, doing a CNO analysis without bismuth constraint. And Borexino unfortunately stops data taking in September this year. So, and there are a lot of other contributions at TAUP. Thanks a lot.